Good day, grade 12 learners. Welcome to today's physical sciences lesson. My name is Thandwe Uwane. This lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center. Today's lesson will be based on electrochemical cells. So we are going to try and summarize what we have done under electrochemical cells, as we know that we are preparing for our prelim examination. Now, you know that this lesson is based on chemistry topic. Therefore, it is very important that immediately when you start with any topic under chemistry, you look at the periodic table. Therefore, we are going to look at our periodic table. Our periodic table is having lots of metals and very few non-metals. It is very important that we remember the properties of metals and non-metals, as we are going to see metals and some of the non-metals gaining electrons and metals losing electrons. Therefore, the properties of metals being able to lose electrons and also being able to be good conductors of electricity, it is very important for this topic, because you know that this topic is about the electron transfer. Therefore, we need to know which elements in the periodic table can be able to lose electrons and which elements in the periodic table can be able to gain electrons as our starting point. Now, we also know that in grade 11, we dealt with oxidation numbers. We need to know the change in oxidation numbers, because when electrons are transferred, there must be a change in oxidation number. Therefore, if the oxidation number doesn't change, it means the electrons are not transferred. Therefore, we need to remember what we did in grade 11 in terms of the change in oxidation number. We need to see whether the oxidation number of a substance has increased or decreased. Now, it is going to be easy if we go back and look at also the rules of oxidation numbers. How do we assign oxidation numbers and see whether those oxidation number of those substances decrease or increase? Therefore, for you to remember oxidation numbers, you need to revise your grade 11 work to check what is an oxidation number and how do we assign oxidation numbers using the rules, so that you can be able to determine whether the oxidation number of a substance has changed. Now, what are the objectives of this lesson? These are the objectives according to the exam guideline. We are going to look at the definition of a galvanic cell, because we are definitely going to start with a galvanic cell and later we'll look at an electrolytic cell. We are also supposed to look at oxidation and reduction definition in terms of electron transfer. We will also have to define oxidation and reduction in terms of oxidation numbers. So that is why it was important for us before we start to go back and revise oxidation numbers of each substance in a reaction. We're also supposed to look at oxidizing agents and reducing agents in terms of oxidation and reduction. And also define our anode and cathode in terms of oxidation and reduction and the definition of an electrolyte. We'll look at how is the potential difference or the cell potential is related to the spontaneity of a cell to reach equilibrium, and what will also decrease the cell potential as the cell is in operation. We'll look at describing the movement of ions in our solutions and also the direction of electron flow in the external circuit. Also look at how do we write our half reactions at each electrode and the function of the salt bridge. We are going to also use the cell notation to represent a galvanic cell, whereby there are bullets that are stipulated on how can we use a cell notation to represent a galvanic cell. We'll predict a reaction where half reaction occurs. We'll start by looking at where oxidation occurs and where reduction occurs, and we'll also be supposed to identify or to write down the overall reaction. We'll also use the standard reduction potential table to calculate the EMF. As you know that this topic is under chemical change, so any stoichiometric calculation can be included as part of the calculations that can be found in this topic. Not only the EMF will be calculated. So we need to remember, how do we use any qualitative aspect to make calculation under this topic. And then we know that positive value, as we are going to calculate EMF, will tell us that the reaction is spontaneous under standard conditions. And we are going to refer to those standard conditions. Know which standard conditions do we refer to that will allow this cell to operate normally, and describe our reference electrode as our hydrogen electrode, and explain why this electrode is referred to as the reference electrode. Now let's go and look at each bullet as it is stated on the exam guideline. Remember, the exam guideline is the guide that will assist us to know the expectations of the examiner as we are going to write our final exam and also our prelim examination, because we know that during prelim exam we are going to write a fully fledged question paper, which is out of 150 paper 1 and 150 paper 2. Therefore, it is crucial that we always refer to the bullets on the exam guideline as we are going to deal with each and every topic and the revision. Now, when we look at our galvanic cell, the first thing they said, we must be able to define it. So we are going to define our galvanic cell using energy conversion, which says is when chemical energy is converted to electrical energy. And we must also know that these galvanic cells are spontaneous reactions. They occur on their own, meaning that there is no energy added for this cell to be in operation. These cells are exothermic reactions because they release energy as electrical energy. So remember, we are going to see electrical energy being formed as this chemical energy is going to be converted. Therefore, we say it is exothermic reaction because electrical energy is released, and exothermic reactions are the reactions where energy is released. Remember, galvanic cells and also electrolytic cells deal with redox, meaning that with electron transfer. So redox means electron transfer because it involves both oxidation and reduction reaction. So when you look at the word redox, it's an acronym for two words, which is red for reduction and ox for oxidation. Now we need to know that it is everything to do with what? With electron transfer. I think by now we understand that when we say transfer, we mean movement in both directions. When electrons are transferred, it means one of the substance will lose electrons and the other one will gain those electrons. Why it is important to refer to the lose and gain simultaneously is because there is no way that a substance can lose an electron without being gained by another substance, because electrons, remember, they are charges. Now, according to the law of charges, we know that charges cannot be lost nor created, but they can be transferred. So that is why electrons are transferred, and there must always be a substance that loses and the other one gaining those electrons. We know that metals, as one of the property, they can lose electrons easily because of their the outermost energy level, and also those delocalized electrons. However, non-metals will not lose electrons, but they will gain electrons. Therefore, we will see many of our metals losing. However, this losing of electrons will not only be subjected to metals, because whenever a metal or a non-metal undergo electron transfer, that metal or that non-metal will definitely change from being a metal to a non-metal to an ion. Therefore, we'll see also metallic ions being able to gain electrons, and also non-metallic ions being able to lose electrons, because immediately when a metal loses an electron, it means it is in an unstable state. Therefore, for it to go back to a stable state, it must gain whatever electrons that it has lost. So that is why we'll see some of the metallic ions gaining those electrons back to form the original metal, which are definitely neutral. So you need to understand that immediately when metals loses electrons or non-metals gains electrons, they will have imbalance in terms of the number of protons and electrons. it will depend whether a substance has lost or has gained electrons. In an instant where a substance has lost electron, what will happen? It means it will have more protons than electrons. So we'll see most of the metals having a charge being positive. However, non-metals having a charge being negative, because it means if non-metals gain electrons, they will have more electrons than protons. Therefore, that is why their charge normally become negative. We are also going to use our metals or our electrical conductors as our electrodes in this circuit or in these cells, because definitely we are going to deal with a circuit whereby we know that those conductors must be good conductors of electricity for them to be able to transfer electrons, or for them to be able to allow electrical conductivity. Now, we need to define oxidation and reduction in two terms. The examiner expects us to define them in terms of electron transfer and also in terms of oxidation number. Now, when we look at electron transfer, oxidation is the loss of electrons and reduction is gain of electrons, meaning where there is oxidation, there will be a substance that will lose electrons. And where there is reduction, there will be a substance that will gain those electrons. Now we can use suffix like Ulrich or Lioke just to remember the definitions in terms of electron transfer. Where we say oxidation is loss of electrons, reduction is gain of electrons. Or we can say loss of electrons is oxidation and gain of electrons is reduction. So we are just using these acronyms so that we can remember the definition of oxidation and reduction in terms of electron transfer, because they are very close to each other. When the other one loses, the other one gains. So you need to say the correct definition according to the exam guideline. Now, in terms of oxidation number, we know that we said immediately when a substance or an atom loses or gain electrons, the oxidation number will change. Now, how will the oxidation number change? Whenever a substance undergoes oxidation, we will see by the increase in oxidation number, meaning that, for example, when we look at zinc metal, we know that zinc metal from the periodic table is the neutral metal, meaning that it's having the same number of protons and electrons. However, because it's a metal, it is having a property of losing electrons. Immediately when zinc metal loses electrons, it changes and becomes zinc 2+ ion. Therefore, it means its oxidation number starts from 0. Why is the oxidation number referred as 0? Is because the net charge is 0. The number of protons and electrons are equal. Immediately when it starts losing electrons, the net charge now changes. There will be more protons than electrons because some of the electrons are being lost. Therefore, it changed from 0 to 2. It means that the oxidation number of zinc has increased. Whenever the zinc 2+, because I said immediately when an ion, a metal become an ion or a non-metal become an ion, is in an unstable state. So it means for zinc 2+, which is a zinc ion, to go back to zinc, it must gain the electrons that it has lost. So when zinc 2+ gain 2 electrons, I'm saying zinc 2+ plus 2 electrons, meaning that we are going to add the 2 electrons on zinc 2+. Therefore, it will go back and become zinc. So the oxidation number changes from +2 to 0. That is why we say during reduction, where the electrons are going to be gained, there will be a decrease in oxidation number. Now let's look at the agents. These are the two agents that will be our reactants. What we need to understand is that the agents are going to be our reactants, meaning there are those substances now that will definitely lose and gain electrons, meaning when one of the agent is losing electrons, the other agent is gaining electrons. However, because they are agents, they will make sure that the processes of oxidation and reduction occur. When you are an agent, you will cause a process to occur without you undergoing that same process. It's like when you have a car agent. A car agent will stimulate you buying a car. However, the car agent will not buy a car, meaning that the car agent will cause the buying to occur. Who is the buyer? The buyer is the person who will definitely buy the car. Now, when we look at oxidizing agent, this is the agent that will make sure that there will be oxidation. However, because it's an agent that causes oxidation, it will not undergo oxidation. So it means it will make the other substance that is reacting with or the other agent to undergo oxidation. So what is it? An oxidizing agent is a substance that gains electrons and will undergo reduction and is the substance that will be reduced. Remember, if I can go back to the zinc 2 plus gaining electrons, you can see that the oxidation number of zinc 2 plus changed from 2 to 0, meaning that zinc 2 plus is being reduced. Reduced means its oxidation number has decreased. Therefore, what makes the oxidation number of zinc 2 plus to decrease is by zinc 2 plus gaining electrons. Therefore, if we are saying an oxidizing agent is a substance that gains electrons, we will expect its oxidation number to decrease, meaning that that agent will be reduced. So we need to know that if you are causing a specific type of a reaction, you will undergo the opposite reaction. Therefore, because an oxidizing agent made oxidation to occur, therefore a reducing agent will make a reduction to occur, meaning that a reducing agent will cause an oxidizing agent to undergo reduction. However, a reducing agent will lose electrons and undergo oxidation, meaning that its oxidation number will increase, and at the end of the day, we'll say it is oxidized. Oxidized means oxidation number has increased. So, we need not to confuse the reactions with the agents. Each agent will undergo a specific reaction. Therefore, it is very important that we know exactly which agent undergoes which reaction. And we need also to identify the agents in our reaction. That means we need to be able to say who is gaining electrons and who is losing electrons. The next term is electrode. As I said, electrodes are solid electrical conductors that will carry electrical current to non-metallic part of a circuit. Non-metallic meaning that it will normally carry it to the solution or our electrolyte, which is the next term that we are going to look at. So we have two types of electrodes that will allow the possibility of electron transfer. We have the anode, which is our electrode where oxidation will occur. And for us to remember, we can use oxen, meaning that ox for oxidation, N for anode. So oxen, oxidation occur at the anode. The next electrode is cathode. Now, our cathode is where reduction will take place. And we can use red cat just to remember that reduction occurs at the cathode. As I said that these are solid conductors, therefore, we'll expect each and every reaction or each and every cell to have the two electrodes which are solid, which will allow the movement of electrons, which will allow the flow of electrical current. So by now we know that electrons will flow through the electrodes and the conductors because they are all solids. So just to summarize, we know that at the anode, that's where we are going to find our reducing agent, which is the agent that loses electrons. and where we are going to find oxidation reaction, and at the end of the day that agent will be oxidized. So whenever you need to identify your reducing agent, you must make sure that you identify your reducing agent where oxidation occurred, because that's where you are going to find a substance that will lose electrons. Whenever there is a cathode site, or where there is a cathode electrode, we'll expect to find our oxidizing agent. We'll expect that agent to undergo reduction, and we'll expect to be reduced after undergoing reduction. And remember, you can only undergo reduction when you gain electrons and when you undergo reduction reaction and your oxidation number decreases. So this is just a summary of what is happening in each and every half cell that we are going to look at. Now, we know that we are going to deal with chemical energy that will be converted to electrical energy. Therefore, we have what we call electrolytes, which are the solutions. I like to take it from here: solutions that contain ions, or solutions that can conduct electricity. We said electrodes conduct electricity. However, what is flowing in our electrodes, because they are solid, is electrons. And in our electrolyte, what it is there is our ions. Therefore, electrolyte is for the solution where there are ions, and electrodes is for the ions because they are solid. So we need to differentiate between electrodes and electrolyte. Always when you need to identify an electrode, you must make sure that that specific substance is a solid. However, an electrolyte must be a solution. Therefore, we will need definitely to see the word solution and solid when you try to differentiate between the two conductors. Now, how do you identify a galvanic cell? A galvanic cell will always have two electrolytes. Normally, our electrolytes are shown by ions. They are shown by ions. However, sometimes our electrolytes can be shown by a compound. Therefore, if you are given an electrolyte like magnesium sulfate, you will know that the ions that are involved is magnesium 2+ ion plus sulfate ion. It qualifies to be an electrolyte because it is having both the positive and the negative ions. What do we refer as our positive ions? We refer to them as our cation ions, and our negative ions we refer to them as our anions. Therefore, you will see a cell having two types of electrolytes, which will make it to qualify for a galvanic cell. They might be inside the beakers, or sometimes they might be in the reaction. However, you need to identify that this cell is having two electrolytes. It is also having two electrodes that are connected by a galvanometer. Sometimes you can use a voltmeter. However, a galvanometer is a relevant apparatus that we can use for the measurement of our voltage, because normally our cells produce a very small amount of current, which may sometimes not be detected by our voltmeter. Therefore, the instrument that is suitable for our galvanic cell is the galvanometer. And those cells also have a salt bridge that consists of a salt. In SSL basis, we've seen how salts were formed. Therefore, already we know what is a salt. And we cannot replace a salt by another substance to make it a salt bridge. Therefore, it needs to be a salt, and it also needs to be a soluble salt. So normally we use our nitrate salts as our soluble salts for our salt bridge. Now we know that a galvanic cell will consist of two electrolytes, electrodes connected via galvanometer, and also a salt bridge. Now, in a galvanic cell, you will find our anode, which is our electrode, and our cathode. We will see that our anode will become our negative electrode, and our cathode will become our positive electrode. When I say become, is because there are no connections in a galvanic cell. We are not going to connect with any power source. Therefore, those electrodes for the cell to operate normally, they will definitely be our terminals. They will definitely be our positive and negative terminal. Now let's look at the table of reduction potential, because this will assist you to be able to identify most of the reactions that are going to occur and the substances that are going to undergo those reactions. I'm using this table 4b not because there is something wrong with table 4a. The only reason is that when you look at table 4b, it's ascending, starting from a small number, ending with a big number. So that is the reason why I'm using it. And for you to remember some of the things that you have done in class, it is also vital that you familiarize yourself with one table. And normally, we familiarize ourselves with table 4b. We start with the lithium at the top. Now, what does this table say to you? This table is having this reversible arrows. These reversible arrows are just saying to us, it doesn't mean that these reactions are reversible. It only means that it is possible that that half reaction can undergo oxidation or reduction, depending on what it is reacting with. When you look on your right hand side, you will find all your reducing agents on the table. Reducing agents. And when you look on your left hand side, you'll find all your oxidizing agents. Why am I saying these are your reducing agents? It's because all this, when you go from this side to the left, there are those substances that will lose electrons. And everything that is on the left hand side is gaining electrons. And remember, according to our definitions of reducing agent and oxidizing agent, we said reducing agents are substances that lose electrons. Therefore, if you read this reaction from right to left, it says to you lithium has lost electron and become lithium ion. So also calcium has lost 2 electrons and became calcium 2 plus. For calcium 2 plus to go back to calcium, it must gain electrons. So you can see that calcium 2 plus and lithium ions are your oxidizing agents, because they are those substances that gain electrons. And also, there is an arrow on the side that shows the strength of reducing and the strength of oxidizing. Now it says when you go from bottom going up, the strength of reducing is increasing, meaning that lithium is the best reducing agent as compared to all the reducing agents that are found on this table. And also it says fluorine, because it's the one on the left hand side and is the one that is gaining electrons, is the best oxidizing agent. So whenever fluorine is reacting with any half cell, we expect fluorine to undergo reaction. So when we are going to use this table, we are going to use it to make sure that we choose the correct half reaction or the correct half cell to undergo the correct reaction. Why are we referring to them as half cells? We refer to them as half cells because they are going to combine together and form one cell, which is going to be our galvanic cell. Now let's look at a structure, just a simple diagram of a galvanic cell. In a galvanic cell, as we said, we are going to have our electrodes, which are connected by a wire, and we normally call this our external circuit. We say it's our external circuit because that is where we are going to see the flow of electrons. It is also vital to know from which side to which side will our electrons flow. So we need to know that our electrons will flow from anode side to cathode side. And we'll also explain why our anode become our negative electrode, as I said, and our cathode become our positive electrode. We'll have the second type of a circuit where we have our Stall bridge connecting our two electrolytes. This we normally refer to it as our internal circuit. what flows in our internal circuit is our ions. So we'll expect our ions to flow inside the internal circuit because that is where we find our electrolyte. As I said that our electrolyte are in a solution form and our electrodes are in a solid form. So therefore, electrodes will conduct electrons and electrolytes will conduct ions. Therefore, we refer to this as our internal circuit. So this is a complete galvanic cell. The example of this galvanic cell is a copper and zinc cell. Why I was saying it's a cell? It's because it combines a half cell of zinc and a half cell of copper. This is a half cell of copper. Therefore, together joined, we refer to them as one full cell of zinc and copper. Now, we need to also know what is definitely happening when oxidation and reduction occurs. We know that what will make the two cells, the two reactions to undergo redox is because one half cell must undergo oxidation and one half cell must undergo reduction. Therefore, let me use the example of zinc and copper for us to know which half cell will undergo oxidation and how does it undergo oxidation. Just to go back to our table. Now, we will firstly use our table to identify which half cell undergoes oxidation and which half cell undergo reduction. What will determine the half cell undergoing oxidation is not anything but the strength of oxidizing and reducing agent. So we know that lithium is the strongest reducing agent, meaning that everything that follows lithium will be weaker than lithium in terms of the reducing strength. Therefore, when we go down, we will know that the strength of reducing is decreasing. Therefore, it means if we compare zinc half cell and copper 2 plus half cell, because we are going to choose copper 2 plus because we have sulfate 2 plus ion, which is this one of 0.34. We will compare the strength of zinc and copper. And we'll firstly ask ourselves which one is the stronger oxidizing, or which one is the stronger reducing agent. And when you compare zinc and copper, you will see that zinc is a stronger reducing agent than copper. Therefore, the zinc half cell will undergo oxidation because zinc is the one that will undergo oxidation because of being the best reducing agent than copper. And what will happen is that when coming to reduction, now we need to look at the site where they are oxidizing agents. And we agree that our oxidizing agents, we are going to read them at the left hand side. So what will happen is that when zinc loses electrons, those electrons will be gained by copper 2 plus ions, which will be our oxidizing agent at the copper half cell. Therefore, it means now, let's look at what will happen at the zinc half cell. If this is our zinc electrode, and inside this zinc electrode we have zinc 2 plus ions and sulfate ions, which are going to have the same number because this is a neutral electrolyte. And we know that zinc will be connected in a galvanometer to the other side. So we are saying now zinc is the one that will undergo oxidation because it's the stronger reducing agent. So what will happen when zinc undergo oxidation? Zinc, as it undergoes oxidation, it is inside a zinc sulfate, which is a non-metallic part of our circuit. It will now dissolve into this zinc sulfate solution and form more zinc 2 plus ion, meaning that zinc as our electrode, which is a solid, will lose electrons and become then N2 plus zinc ion plus 2 electrons. So remember that N2 plus is our aqueous because it's now in an ionic form. So when zinc undergoes oxidation, it will form zinc 2 plus ion. And zinc 2 plus ion will go and be found in the solution. And you can see now that our solution is having more positive ions, meaning that our solution is now more positive. And where are the electrons going? The electrons are going through the conductor to the side where they will be attracted. Therefore, because electrons are being repelled by the zinc electrode, this means that our zinc become our negative electrode because it repels negative charges. We know that light charges repels. So that is why our zinc electrode becomes our negative electrode. And for that fact, it means it's going to be our anode, where oxidation occurs. So therefore, the electrons will travel through our external circuit and go to the side where there is our copper electrode. And inside the copper electrode, according to our diagram, our previous diagram, there were copper 2 plus ion and sulfate ions of equal magnitude because this was neutral. Immediately when now electrons are transferred and they go towards the copper electrode. So this is the direction of electrons. Copper, as our metal, will never be in a position to gain those electrons, but it will transfer it to a non-metallic part of our circuit, which is our electrolyte. Inside the electrolyte, we have our copper 2 plus ion and our sulfate ions. Therefore, because the copper electrode now will be having negative electrons, the copper 2 plus ions will be the one that will have interest of gaining those electrons on top of the copper electrode. And as they are gaining the electrons on top of the copper electrode, they will form copper, because meaning that as the copper 2 plus ion inside the solution are gaining 2 electrons from zinc, what they will do, they will form copper, which is our solid, and the copper, which is our solid, will form on top of the copper electrode that was already there, which assisted in the transfer of electron. So it is very important that you must understand that there is no way that copper as the metal can gain the electrons from zinc, because it is also a reducing agent. The only thing, it can be a good conductor of electricity to be able to transfer electrons to the solution where they will be gained by copper metal, by copper ion, which is copper 2 plus ion. Now you can see that, let me just go back. You can see that the color of our solution was blue. And the reason the color is blue is because of the copper 2 plus ions. So the copper 2 plus ions are the ones that are making the color of copper sulfate to be blue. Now, when the copper 2 plus from our solution are moving away and they are changing, becoming copper, it means the color of our solution will now become colorless, because the copper 2 plus are moving away from the solution, and it means they will decrease the concentration of copper sulfate and the color becomes colorless, meaning that we are now using the copper 2 plus inside the solution. So these are the two half reactions that occur in each apartment, on the side of the anode and the side of the cathode. So to conclude, you can see that the zinc is the one that is losing electrons because its oxidation number changes from Zn to Zn2 plus. And the copper 2 plus is the one that is gaining electrons because its oxidation number changes from Cu2 plus to 0. Therefore, our two reactants are going to be zinc solid, which is undergoing oxidation, and copper 2 plus aqueous, which is undergoing reduction to form zinc 2 plus plus Cu solid. Now, as you can see that when copper 2 plus are going away from the solution, they are making the side of copper to be more negative, as there will only be sulfate ions that are in excess in that electrolyte. Therefore, the imbalance of the two electrolytes in terms of the number of ions will make us not to have a cell that is functional. Therefore, a salt bridge, the function of a salt bridge now, let's say we are using our salt bridge as our potassium nitrate. which is having the positive ions plus the nitrate ions, which are negative, will try and bring the cell neutrality of the electrolytes and neutralize our electrolytes. So we expect that the side that is more positive, which is our anode side, we will expect the nitrate ions, which is our N ions, to flow through that electrolyte. And where there is more negative ions, we'll expect our cat ions to go and neutralize that electrolyte. So we can see that from a salt bridge, we'll see N ions going to the side of the anode and cat ions going to the side of the cathode, just to bring the cell neutrality between our electrolyte. This will occur until our cell reaches what? Equilibrium. And when our cell reaches equilibrium, that is where we say our battery, normally we say our battery is flat, meaning that the voltmeter reading or the cell potential or the V cell is now equals to 0 volts. So we need to be able to say who lost electrons and who gained electrons. And those will be our agents in terms of reducing agents and oxidizing agent. So from this cell, from this reaction, we can see that zinc has lost electrons and zinc become our reducing agent. Copper 2 plus, because it's the one that is going to gain electrons, is going to be our oxidizing or it will complete the circuit, because without a salt bridge, that cell will function a very little time and it will stop because there won't be efficient way of transferring electrons. We are going to go for a short break. After a break, we're going to continue and look at the function of the salt bridge. Welcome back, grade 12s. We were still looking at the functions of the salt bridge, and we said the first one is to complete the circuit, also to allow the ions to flow through without allowing the different solutions to react or to mix, and also it maintains electrical neutrality, as we have seen that the N ions will go into the side of the anode and the cation ions will go into the side of the cathode. So it is very important that we know at least two of the functions of a salt bridge. Now, when the cell is in operation, we said our V cell, which is our electromotive force, will start to decrease. So if V cell decreases, we agreed that it is because there will be an increase in the product, or let me study. There will be a decrease or an increase in the product ion and the decrease in the concentration of the reactant ion. So as you have seen that when the zinc 2 plus ions were going into the solution, which are our product ion, they were causing our cell potential to decrease. And as the copper 2 plus ions that were gaining electrons were decreasing on the other electrolyte, it means it was also affecting our cell potential. So our cell potential decreased because there was a decrease in the there was an increase in the product ions, and there was a decrease in the reactant ion, until our cell reaches equilibrium and we say our battery is flat. Now, as we have already, because we have already looked at how we write our half reactions, we write our half reaction taking them from our reduction potential table. We'll write them as oxidation and reduction. We'll read our oxidation from left to right, so it means our oxidation, we'll read it from left to right, and our reduction, we'll read it from right to left. So our reduction, we write them exactly as they appear on that reduction potential table, because it is definitely read as reduction potential table. We are going to use one arrow or a single arrow that is facing forward, showing that these reactions are irreversible. So if we are writing the zinc half cell and the copper half cell, we are using this table. Let's say I want to write a calcium half cell, and then I want to make it to react maybe with a zinc half cell. What is going to happen? I will see that calcium is going to be a stronger reducing agent than zinc. Therefore, calcium will undergo oxidation and it will be oxidized to calcium 2 plus. Therefore, calcium, it means calcium half cell will undergo oxidation. How do I write it? I will start from this side going to this side. So we write it as C. As you can see, oxidation, we started from this side to this side, and reduction exactly as it is. So it means it's going to be Ca, which is our solid, because there is no ion showing that it's an aqueous, going to, which is our single arrow, Ca2 plus 2 electrons, which is our aqueous. Therefore, the zinc one is going to be Zn2 plus, which is our aqueous. Single arrow again going to Zn plus 2 electrons going to Zn, which is our reduction. So this is going to be our oxidation reaction, and this is going to be our reduction reaction. So we need to know how do we write our oxidation and reduction reaction using the table. And also, we also need to know how do we write our overall cell reaction. This can be an example between zinc and copper half cell, the example that we're giving in terms of electron transfer. This one is a net cell, or normally we call it an overall reaction. An overall reaction now is when we combine the two half reactions to make one reaction. So you can see here that this is an overall reaction, and we don't include electrons anymore. But now you need to be careful that your electrons must be equal for them not to be included, because if you add the two reactions, these electrons will cancel out and we will be left with this reaction because they are in opposite sides. There will be times where you will find that the number of electrons are not equal in your oxidation and reduction reaction. Like, for example, if you are making an aluminum and silver cell, in an aluminum and silver cell, you will find that aluminum will lose 3 electrons, whereas silver ion will only require 1 electron. Therefore, it means 3 of the silver ions must be present to gain electrons from aluminum. Therefore, we need to balance it. We easily multiply the aluminum half cell by 3 and multiply the silver by 1, because this one is 1, this one is 3. We just swap the electrons. And what we're going to get is that aluminum is going to be added to 3 silver. So 3 electrons of aluminum will be gained by 3 silver ions, and 3 aluminum ion will form, and 3 of the silver solid or metal will be formed. So it is very important that when you write an overall reaction, you make sure that your reaction is balanced, and it is easy to balance by just multiplying each electron from each side. Then you will also be required to write the cell notation. So how do you write the cell notation? Our cell notation will write it as easy as A, B, C, meaning that we'll start with our anode side, write a cell bridge, and go to our cathode side. We know that at our anode side, that's where oxidation occurs. At our cathode side, that's where reduction occurs. So there is no way that you can write a cell notation before you identify which half cell undergo oxidation, which half cell undergo reduction. And also, you must be able to know the phases of the reacting substances. And we are going to separate those phases using a line, and we normally call it as a phase separator or phase boundary. So a cell bridge will be represented by a double line, which will separate the side of the anode and the cathode. Let's look at the example of a cell notation. This is an example of a cell notation of zinc and copper half cell. What you must know that all your solids must be on the terminals, meaning that you start with your solid, you end with your solid. And then all the aqueous must be next to the bridge, meaning that you will start with an oxidizing agent, a reducing agent. If that agent is active electrode, I will explain what do I mean by active electrode. And then we'll go to an oxidized species. And then you go to a cell bridge, because we are just saying zinc solid has changed to zinc 2 plus. What makes the zinc solid to change to zinc 2 plus is because there was oxidation reaction. Then copper 2 plus will gain electrons and form copper. So we know that our copper 2 plus was our oxidizing agent. So you can even use your overall cell reaction to write your cell notation, because you know that you will start with the solid and end with the solid. You will start with your reducing agent and end with your and after the salt bridge, write your oxidizing agent. Now there are times where you find that a half cell doesn't have let me just go back a little. There are times where you'll find that your half cell doesn't have an electrode, doesn't have a solid, like this one, the chromium 2 plus, chromium 3 plus half cell. Let's say this chromium 2 plus, chromium 3 plus is reacting with nickel half cell to undergo oxidation and reduction. Obviously, the Cr2 plus is on the right hand side, meaning is our reducing agent, and also nickel, but this one is going to be our stronger reducing agent as compared to nickel. So Cr2 plus will undergo oxidation and nickel will undergo reduction. Therefore, you will start by writing the oxidation reaction, which is going to be that one of Cr2 plus, which is our aqueous, going to Cr3 plus, which is also our aqueous, plus electron, as indicated on this half cell. And then our reduction will be nickel 2 plus aqueous, which is our ion, plus 2 electrons, giving you nickel solid. So now, when you look at the chromium 2 plus half cell, you can see that we don't have a solid, and we know that for us to represent an electrode, our electrode must be a solid. Therefore, in such cases, when we write our cell notation, we need to provide a solid for that cell, and we normally provide platinum as our inert electrode for such half cell. So if you write an overall reaction, overall is gonna be Cr2 plus plus Ni2 plus, giving us Cr3 plus plus Ni. So this one is our solid. So a nickel half cell, it does have a metal, it does have an electrode. It doesn't need to be provided with an electrode. However, the one of chromium needs. So if you write the cell notation now, you need to provide this. And I said we're going to provide it a platinum electrode. So it's going to be platinum and then phase separator, because platinum is solid and chromium 2 plus is aqueous. And then it's going to be Cr2 plus, which is our aqueous. And we know that after it has lost electron, it became Cr3 plus, which is another. So therefore, because the phases of Cr2 plus and Cr3 plus are equal, we are no longer going to use the phase a phase separator, but we are going to use a comma. It is very important that you remember we use the comma for an aqueous to aqueous or solid to solid. It's very important that you use a comma or gas to gas. And then we're going to have our Stall bridge, and then we're going to have our nickel 2 plus, which is our aqueous. And because it's having a different phase with nickel solid, it's going to be nickel solid. So you can see that even in this one, whenever we have an inactive electrode, we'll still have a solid at the beginning and a solid at the end, because chromium 2 plus cannot act as a conductor because it's in a solution form. So we need to provide, especially when we are showing our cell notation. And we also need to know that even if we can balance, because we can see that here is 2 and 1, we can see that our chromium will definitely be 2 and 2. We don't include our balancing when we are writing our cell notation. We only balance when we do the overall cell reaction. So you can see that platinum doesn't undergo any of the reaction. It is an inert electrode. It doesn't undergo oxidation. It doesn't undergo reduction. Therefore, we cannot expect the mass of platinum to decrease because it never dissolved into any solution. The only function of platinum, it was in electrical conductor. It was transferring electrons from the site of oxidation to the site of reduction. That is very important. Then, okay, so this is exactly how we write our cell notation. Then we can see that even when you have an activity like this one, where you have ion 3 plus, ion 2 plus half cell and hydrogen half cell, you need to look at the spaces that are given in your half reactions for you to choose the correct reaction. There might be more than one half reactions of ion, but you need to say which one exactly must I choose, looking at the spaces in both sides. However, we know that hydrogen half cell is one cell. So you might be required to do this activity maybe, and write down the oxidation and reduction half reaction. So our starting point definitely will be our table. So we will look at the iron 3 plus and iron 2 plus half cell, which is this one, and our hydrogen half cell, which is this one. And when we compare the hydrogen gas, we compare it with iron 2 plus, we can see that hydrogen gas will be a stronger reducing agent. Therefore, it means hydrogen half cell will undergo oxidation, which means it will be hydrogen gas undergoing oxidation and forming H2 plus, which is our aqueous, plus 2 electrons. And our reduction will be exactly as it is, iron 3 plus aqueous plus an electron going to iron 2 plus, which is our aqueous. The reason why I'm always referring to the phases is because it will assist us, especially when we write our cell notation. Therefore, the electrons are not equal. When we write our overall, we need to make sure that our electrons are equal. So it means it's going to be H2 gas plus 2 Fe 3 plus aqueous, giving us 2 Fe 2 plus aqueous plus 2 H plus. Doesn't matter whether we start with an H plus. So this is our overall reaction. Therefore, now if you have to identify your reducing agent and your oxidizing agent, we know we're gonna look this side. This one is from 0 to 1, so it means it's our reducing agent. And then this one is from 3 to 2, which means it's our oxidizing agent. And we already know when we say reducing or oxidizing, which one loses, which one gain electrons. Then in terms of the cell notation, we can see that both our half cells do not have electrolytes. Therefore, we need to provide our anode and our cathode. So it means we're going to provide platinum as our solid phase boundary on our hydrogen half cell, hydrogen gas, and then 2H plus aqueous. So we are done with the anode side, and then salt bridge, and then we have Fe 3 plus. Remember, we don't include balancing, and then because the phases are the same, comma Fe 2 plus, and then it's also an aqueous, and then we don't have a cathode, so we're gonna provide platinum as our solid. So we need to always practice how do we write cell notation where we have an electrode and where we don't have an electrode. So let us not confuse our electrodes with our agents, because in this case platinum is our anode. However, hydrogen gas is our reducing agent. So a reducing agent is not always your anode. And there is no way that your oxidizing agent can be your cathode, because remember, a cathode is an electrical conductor. Normally it's a metal. So there is no way that a metal can gain electrons. But let us not confuse a reducing agent with our anode. And in this case, our cathode will be our platinum will also be our cathode. So both our cathode and anode in this reaction or in this cell is platinum. So here is what we were talking about. This is what we were explaining. We needed to identify our oxidation and reduction, identify our anode and cathode, and we find that it is platinum solid in both. And then we also did our balance equation, and we identify our reducing and oxidizing agent and our cell notation. Now we are also required to remember to calculate the EMF of a cell. So how do we calculate the EMF of a cell? We will only calculate the EMF of a cell in under standard conditions. What are those standard conditions? The standard conditions are provided on our next slide, whereby we are going to find our temperature being 298 kelvins or 25 degrees Celsius. We must know that 25 degrees Celsius is not 273 kelvins. We need to remember how do we change from kelvins to degrees Celsius or from degrees Celsius to kelvins, because normally there are lots of mistakes that learners make in terms of changing the converting degrees Celsius to kelvins. Our pressure can be 1 atmospheric pressure or 101.3 kilopascals. and our concentration is 1 mole per decimeter cube. So these are the conditions that we are going to use to calculate our EMF. And remember, when the value of EMF is positive, it says our reaction is spontaneous. So which formula are we using to calculate our EMF? We can use E theta cell, which is equal to E cathode minus E anode, or E theta cell be equal to E reduction reaction minus E oxidation, or E theta cell equals to minus E theta oxidizing agent minus E. So you can see that at the cathode, that's where you're going to find your reduction reaction, and where you are going to find the the oxidizing agent. At the anode, that's where oxidation reaction will occur, and you're going to find your reducing agent. So it is very, you can even use this table to remember these type of reactions and these agents, where you will find at the anode and where you will find at the cathode. What you must also know is that when you write these reactions or these equations, they must be in full. We don't make abbreviation. Copy the formulas as they appear on the data sheet. We always say physical science is the only subject where you go to the exam room with crib notes, because you will copy the formula and get a mark for copying the formula correctly, and also use the formula, because you cannot just copy the formula and not use it. For you to qualify for a mark, you must copy the formula and use it, meaning that you must substitute on that formula. So this is how we are going to calculate our EMF. We have spoke about the standard conditions of calculating EMF, or of the normal functionality of a galvanic cell. Now, we have seen that our cell potentials, or our half cell has cell potentials. So how were the half cell potentials determined? They were determined by connecting them to a reference electrode of hydrogen. Hydrogen is cell potential is 0.00 volts. Therefore, whatever half cell that was connected to a hydrogen half cell, which is our reference electrode, we were able to find the cell potential of that half cell. So all the values that you see on that reduction potential table were determined by them being connected to a hydrogen half cell. And you can see that we are using platinum foil as our electrode, because hydrogen half cell doesn't have an electrode to connect, so this will connect to another half cell. And the conditions are hydrogen at the pressure being 101, the temperature being 298, and the concentration of the electrolyte being what? Being of sulfuric acid, which is, they were using sulfuric acid because, as we know, that sulfuric acid is a strong conductor of electricity, or it can release hydrogen ions from the information that we got from acids and bases. So they use it as our electrolyte, which has 2H plus ions. Therefore, as a diprotic acid, so they used it as our electrolyte, and its own concentration was 1 mole per decimeter cube. So that was our reference electrode. So as I was saying, that all these values were connected to hydrogen to be allocated to each half cell, and you can see that hydrogen half cell is separating all the positive and all the negative half cells in that table 4b. Now let me just pass this one. Let's look at this activity just to see whether we can recap on what we have done. Consider the electrochemical cell with the following cell notation. So you might be provided cell notation, you might be provided overall reaction, or you might be provided the diagram. You need to be able to use all those forms of questioning in order for you to answer questions on galvanic cell. So here you can see that we are given a hydrogen half cell and an iron 3 plus to iron 2 plus half cell, and in both reactions we can see we are having our platinum as our conductors or our electrodes, because the two half cells doesn't have. So when we said we write a cell notation, we said we write it as A, B, C. So this is the anode side, the bridge, and the cathode side. Now we need to look at the question, which one of the following equations represent a cathode half reaction? So we will definitely look at the side where there is C, which is our cathode side. Now we need to know that in a cathode side, what happened? Ion 3 plus gain electron and become ion 2 plus, meaning that ion 3 plus was reduced to ion 2 plus. Therefore, if we need to look at the distractors, there's no way that A, C, and D can be any of the distractors because they are both falling at the anode side. So the only distractors that we can look at is A and B. And if you look at A, it is ion 3 plus going to ion 2 plus, whereby it means there was a decrease in what? In oxidation number. But when you look at B, is 2 plus going to 3 plus, which there was an increase in oxidation number. And we expect at the cathode to find what? Reduction. Therefore, it means the number B is incorrect because number B actually represents oxidation reaction. So the correct answer is number A. Let's look at another activity where we are looking at a cell notation again. We have nickel half cell, a bridge, and a silver ion half cell. Now, what we need to know is that when we are given any half cell in any form, we need to take it back to oxidation half reaction, reduction half reaction, and also cell notation. So they say here a bulb connected across the two electrodes glows brightly. After some time, the brightness of the bulb decreases. So immediately when they talk about the brightness of the bulb, what can affect the brightness of the bulb is when the cell potential decreases. Because it means now the energy released or the number of electrons that are released by the cell, they are decreasing. So this is because of, before you can even try and respond to such a question, you need to remember what decreases the cell potential. We said the cell potential decreased because of the increase in ions. Therefore, we need to say between the nickel ion and the silver ion, which one is our product ion and which one is our nickel reactant ion. From here, you can see that this one, our nickel, is our reducing agent. Therefore, it means it is going to lose electron and form nickel 2 plus ion. So it means nickel 2 plus ion are the ions that are formed, so they are the product ions. However, those electrons that are lost by nickel, they will be gained by silver ion, which is our oxidizing agent. And as our oxidizing agent is also our reactant ion. So we expect now this one to increase in terms of the concentration and this one to decrease in terms of the concentration. So let's say the silver electrode is used up. There is no way that silver electrode can be used up because definitely silver electrode is formed when a silver ion gain electron. Nickel electrode is used up. Nickel electrode cannot be used up even though the mass of nickel will decrease, but it will never be used up in this reaction. Now, concentration of silver ion decreases. What are we expecting? We are expecting the silver ion concentration to decrease. This must be a correct statement. Let's look at the last one. The concentration of nickel ion decreases. Definitely incorrect because what will decrease the cell potential is when the concentration of the nickel ion increases. So the correct answer is C. As we say here, that the cell potential decreases because of the product ion increasing and the reactant ion concentration decreasing. So silver ion, as they decrease, they are the reactant ion, so they will decrease the cell potential. Now, as I said, you might be provided also with what? With the diagram. Now, in this diagram, we are told that the diagram below represents a galvanic cell functioning under standard conditions using a silver and an unknown metal. So we don't know what is this metal. It's unknown. So we don't know what is the half cell of silver reacting with. But we are also given the information that the initial reading of the voltmeter is 0.93 volts. Now, what is the clue that the examiner has given us? The examiner has given us the direction of electrons. The electrons are moving from M, which is our unknown electrode, to silver, which is the known electrode. So it means if the electrons are moving from this side, it means this side is where oxidation occurs. And also it will tell us that our metal M is our anode. Therefore, if our metal M is our anode, therefore silver is going to be our cathode. So the direction of electrons here, it was the only clue to know which side is oxidation and which side is reduction. And we are having our electrolyte silver plus and M2 plus. Now they say which electrode is the cathode. Obviously, because the electrons are moving from this side to this side, we know that they move from the anode to the cathode. So our silver, which is Ag, is our cathode. Identify metal M by referring to the calculation. So now we know that when we do calculations, we will look at the formula that we are going to calculate EMF with, because we provided EMF as 0.93. We know the half cell of silver is 0.93. We got it from the reduction potential table. Therefore, we know that already this one is our anode, our M is our anode. So we'll calculate and find the E oxidation, which is going to give us negative 0.13. And when we go to the reduction potential table, we will find that 0.13 is our, we can go to our reduction potential table. 0, so you look at the values here. You look at the values and you'll find that negative 1.3, this one, negative 0.13 is here. And our metal is nickel, Pb. So that is why you will conclude to say metal M, which was provided, is our Pb, which is a lead. And for that is 5 marks. So it's 1 mark for the formula, 1 mark for substitution of 0.93, 1 mark for getting or solving the value of M, and also a mark. Now, the other question says, our salt bridge is now filled with sugar solution. As we said, there's nothing that can replace a salt. If they fill a salt bridge with sugar, it means now our salt bridge is no longer capable to allow the movement of ions. So the voltmeter reading, we expect it to be 0 volts, because if the ions cannot move, there won't be any electron flow. Okay, so we expect our voltmeter reading to be 0 volts. In this one, we have oxygen and hydrogen peroxide cell. So you will see always that you will be given species, and you need to identify your species of your half cell for you to choose the correct half cell. So you'll definitely go to the table again and check which half cell is gonna be of oxygen, and definitely, sorry, for copper, it was easy for you to determine. Therefore, you will answer the questions looking at the, just go back, looking at the 12 cell. You will also identify your anode and your cathode. But when you look at the two, you will see that this one will undergo oxidation when you look at the table, and this half cell will undergo reduction. And if this half cell undergo oxidation, therefore your cathode will be your platinum, because the half cell of oxygen to hydrogen peroxide doesn't have an electrode. Therefore, we are going to provide it with the cathode, which is a platinum. And then our oxidation is going to be this one of copper going to copper 2 plus 2 electrons. And then our reduction, of course, is going to be that one of oxygen, our overall or balance cell, and our cell notation, and also our EMF. So all these are the responses of what was asked on the previous slide. So this is just a practice to assist you to be able to understand what is a galvanic cell and how can you answer questions on a galvanic cell. And then this one is also a way of asking a galvanic cell. In this one, we are given just a table of half cell A and half cell B. So what will make you to see that this is the galvanic cell? There are 2 electrolytes, which is copper 2 plus, and Ag plus. So already, because there are 2 electrolytes, it will already tell you that this is the galvanic cell. So they said the table below shows half cell A and half cell B. used to assemble an electrochemical cell under standard condition. And you can see that standard condition is written in capital letters. So remember the condition: C being equals to 1 mole per decimeter cube, temperature being equals to 25 degrees Celsius, and pressure being equals to, but you can see that there is no gas here, so definitely pressure will not be part of the conditions that will affect this cell. So the first question says state energy conversion. Because we have identified that it's a galvanic cell by looking at the two electrolytes, therefore you will explain it as chemical energy being converted to electrical energy. Now, as I said, that we sometimes include these calculations because this is under chemical change. Here they say calculate the mass of silver nitrate used to prepare 150 cubic centimeter of the electrolyte of B. So this is just an integration of a calculation with this topic. But now, how do we determine the mass? We know that to determine the mass, we must definitely have what? We must definitely have the molar mass. We must definitely have the number of moles. So when we want to use the formula N is equals to mass over molar mass, we definitely need to find the number of moles. So how do we find the number of moles? You are provided with the volume, and you are also provided with the standard condition, which is our concentration. Therefore, for you to calculate the number of moles, you know that N is equals to, or we can say C, because I like to use the formulas as they appear on the data sheet. C is equals to N over V. Our volume is given in cubic centimeter. We know that we divide by 1,000 for us to find cubic decimeter, which is going to be, our concentration is 1 because of standard condition, and our volume is going to be 0.15, and our number of moles is going to be 0.15 moles. Therefore, it is very important that you know that sometimes the information or the numbers can be given as words. So as the standard condition was given as one of the conditions, we were supposed to use that information of the standard condition to determine our concentration. So you can see that we're going to calculate our number of moles, which is 0.5, and after that we calculate the molar mass of silver nitrate, which is silver is 108, nitrogen is 14, and there are 3 oxygen, which is 16 times 8, which is 16 times 3. Therefore the molar mass of silver nitrate is 170 grams per mole, and then when we substitute it in the formula of N is equals to M over M, we're going to find the mass of this, the mass of the electrolyte as 25.5 grams. The next question says define a reducing agent. We know that a reducing agent is an agent that a substance that loses electrons, or is a substance that is being oxidized, because we know that after losing electron is also going to be oxidized. Name or formula of a reducing agent. Immediately when you are able to determine which formula will undergo oxidation, which is definitely going to be copper half cell, you will find that copper, because there's a name or formula, copper being our reducing agent. And then the balance equation, you will add the formula of copper and silver. So in terms of this one, it's going to be copper, which is solid, which undergoes oxidation, plus silver ion, which undergo reduction. But remember, copper is providing 2 of the electrons, so there will be 2 electrons that are getting, 2 silver ions that are getting each electron from copper, and then they will give you copper 2 plus ion, which is our aqueous, and also our silver, which is our solid. But remember, there will be 2 silver that are formed from the copper. We can also calculate the initial EMF, because we are going to use the reduction potential table to find the values of the copper cell and the silver. The silver is 0.80 and the copper is 0.34. So we'll subtract using the correct formula and subtract and get the correct answer. How will the EMF of the cell be affected if the concentration of copper of the copper ions in half cell A increases? Now, when we look at our copper ions, you can see that these copper ions are our product ions. So we expect the concentration of the product ions to increase and the concentration of the reactant ions to decrease, which will make our cell potential to decrease. So if we increase the concentration of copper 2 plus ion, we are increasing the product ion. Therefore, we are expecting the concentration, the EMF of the cell to decrease, because as you increase the concentration of the product ions, you will decrease the EMF of a cell. The only way to increase the EMF of a cell is by us increasing or adding the silver nitrate solution, which will be our reactant ion, and that will increase the cell potential. And we can also explain this using our Le Chatelier's principle to say what will definitely favor the forward reaction by increasing the concentration of the reactant. So these are the possible solutions for our question. Reducing agent is the substance that loses electrons, and I also included the weight is the substance that is being oxidized. And then this is our reducing agent, as we have identified that copper will undergo oxidation reaction. This is our overall reaction from our question, and here we were calculating the EMF of the cell, and we have seen that the EMF of the cell was positive, meaning that this cell was spontaneous, and this shows that this is a galvanic cell. As the concentration of the product ion increases, we expected the EMF of a cell to decrease. So this is the information that we've been using in order for us to understand this question. We have come to the end of our lesson. I hope you have gained a lot from this lesson. If we can go back and recap on what we have done today, we looked at how oxidation and reduction occur. We look at an oxidizing agent and a reducing agent as our reactants that will lose and gain electrons. We also looked at how do we write each half cell using single arrow facing forward and our overall reaction, and balancing them where it is necessary in terms of the number of electrons not being equal. We also looked at our reduction potential table, which assisted us to identify our oxidizing agents and our reducing agents, looking at both sides. And we also look at the strengths of our oxidizing agents and our reducing agent, which will assist you to understand why when we are having two half cells, the other one undergo oxidation and the other one undergo reduction, and why the other reactant is being oxidized and why the other reactant is being reduced. We also look at how do we write our cell notation, and also how do we provide the electrode in half cells where there were no electrode. We also look at how do we calculate the EMF of a cell, and also how do we calculate or determine the electrode if an EMF of a cell is provided. So from this whole information that we've discussed, I will expect you to go back and look at previous question papers and try to answer questions on a galvanic cell and see whether you can be able to answer questions on galvanic cell. Thank you so much for watching this lesson. Please remember, we are preparing for our exam, which is our prelim and ultimately final examination. From my side, thank you so much and goodbye.